Hi, welcome to this short presentation reviewing material from Geology 1030. This presentation does not include everything that could possibly be on your final exam. However, it should help remind you of the myriad things we've covered throughout the semester because it's a very far-reaching course, especially considering that it's 1 credit hour. Geology is a big field, and we've looked at things in a lot of different areas. We started the semester looking at topographic maps. This is because it can help us to interpret the topo maps that we see when we go on different field trips. The important thing to remember about topographic maps is that they have contour intervals. These show the amount of elevational change that occurs between each adjacent contour lines. So where contour lines are very close together, that's an area of very steep elevational change, and where contour lines are far apart, that's a flat region. Minerals are naturally occurring inorganic crystalline solids with a fixed chemical composition. A rock, in contrast, is comprised of one or more minerals. Minerals can be identified through luster, cleavage, fracture, streak, and hardness, and Bowen's reaction series is shown on the left. So if you'll remember this, we've got very dark minerals at the top. These are low in silica. These are susceptible to chemical weathering, and they have a very high temperature of crystallization. Towards the bottom, we have more felsic or high in silica minerals that are less susceptible to chemical weathering, lower in temperature of crystallization. So remember, it's felsic minerals at the bottom, mafic minerals at the top. I really believe that Lab C, or geologic time, is sort of the key to this whole semester. We talked about absolute dating. So this is the idea that radioisotopic composition of different minerals and things trapped inside rock layers can tell us their exact ages. But I think more importantly, we learned about relative dating. It's these principles. They're actually pretty straightforward from a scientist several hundred years ago named Steno. But together, these 5 principles can help us to interpret almost all depositional environments and landscapes. So there's the principle of original horizontality, which is that sedimentary layers will originally be deposited horizontally. If you find that they are no longer horizontal, that means that some type of tilting has occurred after they were deposited. I think the most important thing in the whole semester is the law of superposition. This is just older sedimentary rocks are below younger sedimentary rocks. There's the principle of lateral continuity. You can expect a sedimentary layer to extend in all directions, thinning on the sides. There's the principle of cross-cutting relationships. So this is also sometimes called the principle of intrusions. If you have something cutting across several layers, whether that be a fault or an igneous intrusion, that intrusion or thing that cuts across will be younger than the rocks it cuts across. Finally, you have the principle of inclusions. Bits of rock included in another layer must come from a rock that was already there. Therefore, the inclusions come from an older rock than the rock that they are included in. Lab D covered plate tectonics, which is one of the great unifying theories of geological sciences. There are 3 primary types of plate boundaries, but we divide convergent boundaries into subduction zones and continental collisions. So you've got convergent boundaries where 2 plates come together. You've got divergent boundaries where 2 plates move apart from each other. And finally, there are transform boundaries where 2 plates slide past each other. These plates are parts of the lithosphere, or the Earth's crust and upper mantle, that move together. But subduction regions, plates move towards a boundary, and one plate slides underneath the other. It will be an oceanic plate that goes underneath the other plate, which can either be oceanic or continental. In continental collision boundaries, you have two continental plates that move together. These areas, such as the Himalaya, have very high mountains. Subduction regions are characterized by having very deep earthquakes. Divergent boundaries are areas where new crust is being formed. This can occur at mid-ocean ridges, such as the Mid-Atlantic Ridge, or it can occur in continental rifting regions, such as the East African Rift Valley. Finally, transform boundaries, such as the San Andreas Fault in California, involve plates moving parallel to a boundary but in opposite directions. These boundaries are characterized by having a lot of shallow earthquakes. In Lab E at Flagstaff, we got to see a lot of different formations from the Boulder region. So first we saw the Boulder Creek granodiorite, which is one of these older granitic rocks that dates to about 1.7 billion years, around the time of the formation of this region as continental crust. Next, we saw the Fountain Formation, which the Flatirons are made of. This is comprised of sandstone that was formed from the weathering of the ancestral Rockies. That environment changed. The ancestral Rockies weathered away. The area became full of sand dunes. And then that formed what we found in the Lion Sandstone, which is what all of the buildings at CU basically are made of. It's more yellow in color compared to the red of the Fountain Formation. We didn't see the next several formations at Flagstaff, but we did see the Niobrara Formation, which comes from the Mesozoic, the Cretaceous actually, inside the Mesozoic, when this region was covered by a shallow sea, the Cretaceous Interior Seaway. At Flagstaff, we talked about different types of rock contacts. These can either consist of faulting, places where there's a tectonic boundary. These can consist of igneous intrusions, places where an igneous rock is encased within a different rock formation. If you remember Ralston Buttes, which we saw, which was totally encased within the Fountain Formation. Rock contacts can be conformable. So there is not a large time boundary between two conformable layers. They'll both be sedimentary. It's just that the environment changed, and so the actual rock is different. You can see the dark rock inside of the lighter layers, but there isn't anything really dramatic or any stark time that occurred between these. Finally, there are unconformities. These represent gaps in time. Something happened. The angular unconformities are probably the easiest to recognize because the rock layers underneath the unconformity are all tilted a different direction from the rock layers directly above them. A disconformity is the most difficult to identify. Geologists typically only can identify disconformities when they find that the layers below this have fossils from a much earlier time period than the fossils in the layers above them. Disconformities happen between two sedimentary layers, but there's a very long time gap between them. Finally, there are nonconformities, and these are identified by the fact that the lower layers of rocks will either be igneous or metamorphic, and the layers on top will be sedimentary. So we saw an example of a nonconformity in what in this region is called the Great Unconformity, which is between the Boulder Creek granodiorite, which is 1.7 billion years old, and the Fountain Formation, which is 300 million years old. So we know there is a long time gap, and because the Boulder Creek granodiorite is igneous, it's technically classified as a nonconformity. We saw a number of different Mesozoic environments. So the Mesozoic is the time of the dinosaurs. The Morrison Formation was this like kind of yellowy, red colored sandstone from about 150 million years ago, so the Jurassic. There were different sandstone lenses that showed us channel migration, indicating that this was a floodplain environment, that there was a river here. We saw some cool fossils, including just fossilized footprints of bulges from dinosaurs walking over this fairly soft environment. Next, we saw the Dakota Formation from about 100 million years ago, or the Cretaceous. Black shales in this environment indicated that there was organic carbon in an anoxic environment. We also saw ripples, indicating that this might have been a marine environment. But then we saw all of these fossils, especially of footprints, indicating that this was likely a coastline of what we call the Cretaceous Interior Seaway. This seaway would sometimes recede, and then it would be called a regression, and sometimes the sea level would rise, and it would be called a transgression. The Benton Formation from about 80 million years ago, still the Cretaceous, was made of shale and mudstone. It was from a much lower energy depositional environment, indicated that there had been a transgression or a rise in sea level in this Cretaceous interior seaway at the time of the Benton Formation's formation. At Jamestown, we looked at environments that were rich in materials that could be mined. And because they had been mined, we were able to see evidence of the environmental destruction that occurs due to what's called acid mine drainage. So hydrothermal alteration is a type of metamorphosis. In these rocks, you can see the yellow rocks in the center picture. There was a passage of mineral-rich fluids associated with magma that intruded 75 to 45 million years ago and left the rocks yellow and sulfur-rich. These sulfur-rich rocks often included exotic minerals that were very appealing to miners. And so areas with this hydrothermal alteration were prime targets for 19th century mining. After mining occurred, sulfuric acid was left in areas that were mined. And so these areas were likely to get sulfuric acid into the water, and it was likely to become very low in pH or very acidic. So you'll remember that 7 is the pH of something that is neutral. 6 is 10 times more acidic than that. 5 is 10 times more acidic than that. And 4, finally, is 1,000 times more acidic than neutral water. So in this pond, we saw water that was around a 4 in pH. You'll see the water there is pretty orange. And that's a very common result in areas with acid mine drainage. At Nederland, we got to see some very cool glacial landscapes. One thing we saw was the Continental Divide, which is the area where you have the divide between the watersheds, whose water ultimately flows into the Atlantic, versus water that ultimately flows into the Pacific. Next, in one place, we got to see where U-shaped valleys and V-shaped valleys intersected. So we saw the end of one area that had been glaciated, and so it was U-shaped as a valley. Remember, glaciers, they're big. They can't flow as quickly as water can in order to like sink to the lowest part of a valley. So we saw a U-shaped valley in the area where the glaciers had covered, and then finally after that, where the glaciers didn't go that far, it was V-shaped. Glaciers also, mountain glaciers particularly, leave some very unique landscapes, such as cirques, which are amphitheater shaped, or arêtes, these really steep ridges. If two arêtes meet and you have just like one steep area that's called a horn. And then you've got roches moutonnées, which are much steeper on one side than on the other. And the roche moutonnées at Netherlands was where we saw glacial polish. In Lab L at Boulder Creek, we talked about flooding. So the recurrence interval is the amount of time that on average is going to elapse between two occurrences of the same river discharge. It really has more to do with probability than the exact number of years that are happening between each flood. You can have a 100-year flood 2 years in a row. It's just fairly improbable. So a 100-year flood has 1 over 100 or 1% chance of happening every year. Whereas like a 10-year flood has a 1 over 10 or 10% chance of happening every year. You can see the discharge graphed against the recurrence interval in that upper right graph. On the left, though, you'll see a Hjulstrom diagram. So this is a graph that records the river velocity necessary to entrain different sediment grain sizes in the water flow. So this is how like very, very large rocks being deposited in a river can indicate that they were transported by very fast water flow. In Lab N, towards the beginning of the semester, we talked about these different types of rocks. So igneous rocks are formed from lava or magma cooling. These can be intrusive, they can be formed inside the earth, or they can be extrusive and be formed on the outside of the earth. Sedimentary rocks are formed from particles of other material. So clastic sedimentary rocks are formed from previous rock material. This can be of different sizes. So like sandstone is from clasts the size of sand, whereas mudstone is from clasts the size of mud. Or they can be biochemical, such as limestone. So these little bits of biochemical particulate form the rocks. Metamorphic rocks are formed from other rocks that have changed. We can divide metamorphic rocks into foliated rocks, which have a characteristic banded or striped pattern, and non-foliated metamorphic rocks, which don't. In Lab N, we discussed climate change. The greenhouse effect occurs because certain gases, called greenhouse gases, including carbon dioxide and methane, as well as nitrous oxide and even water vapor, act so that they allow shortwave radiation, so visible light and UV radiation, from the sun to enter the Earth's atmosphere and warm the Earth's surface. However, when infrared radiation emitted from the Earth's surface attempts to leave the Earth's atmosphere, these gases trap some of the heat in the atmosphere and reflect it back towards the Earth's surface, warming the Earth. The greenhouse effect is not inherently evil or anything. In fact, without it, the Earth's mean temperature would be about 0 degrees Celsius. 0 degrees Fahrenheit. The current issue is that we are increasing the amount of greenhouse gases very rapidly through anthropogenic emissions of CO2 from the burning of fossil fuels, which very rapidly increases the amount of heat being trapped in the atmosphere, making the Earth's increase in temperature very rapid compared to historical rates of change that we can understand through paleoproxy records. So anyway, thanks for listening to this presentation and good luck on your exam.